Okay, so to recap, we are discussing the exam, and we are discussing whether to have negative points for wrong answers or negative points for no answers. And the rationale for that discussion is that we will have questions which will have multiple answers. So for example, we have a question which has 4 answers, 2 of which are correct and 2 are incorrect, right? So if you were to tick the boxes, and if we didn't have negative points for wrong answers, what would be your strategy to tick the boxes in those cases? To tick all of them, exactly, right? So you tick all of them, say, well, you know, and then those 2 are correct, you get 2 points, and those were incorrect, and you know there is no penalty for doing wrong answers, so you get 2 points, and everybody would do that, right? Radio button. So that's wrong, right? So we have to have some discount for somebody ticking the wrong answer here, right? So what would you do?
You can't put in that you can only answer 2 of them.
You can, right? You could restrict that you can only tick 2, right?
Because if it says in the test that only 2 of them is correct, then...
Yep, we could do that. So that's one option. The other one is we give +1 for correct and -1 for incorrect. So then if someone ticked all of 4, we'll get 0. If someone ticked the good ones, we'll get 2. And then if someone ticked the bad ones, we'll get -2 only, right? And so all 2 wrong, 2 good. And then if someone didn't tick anything, should it be 0?
Yes, because then you have equally like no idea as if you ticked all of them.
Well, but if you ticked all of them, you took an action. If you didn't,
you have no idea what you're doing if you're taking all of them. Equally, you have no idea what you're doing. If
yeah,
you're any of them.
Exactly. So is it really equal? Yeah.
The thing is, if you have only 1 correct and 1 incorrect, you should still get, in my opinion, at least a point, because you have at least partial knowledge of the question. Maybe not, it's not entirely correct, but at least something you got right instead of getting 0 points.
Yeah, that's a good point. So what you're saying is if I have okay, so there is only 1 correct, but you ticked 2, 1 wrong and 1 correct. But there was only 1 correct, so the maximum you could get for this was 1. But because you take the other one, the discount should be like half, maybe, right? That's what you're suggesting. Because if someone takes the good one only without taking anything else, obviously that person should score the highest.
Yes.
And the one who ticked something wrong should not score the highest. So there should be some sort of discount, right?
But if there is only 1 correct, it should be allowed only to mark 1 answer, in my opinion.
Okay, why?
Because then you can't just take several and guess. So like if you can mark 2, you can at least get half a point if you got it correct.
Yeah, so obviously we will have radio buttons questions where you can only tick 1, right? That's the traditional multi-choice where you just have 1 and that's it, right? And then you either get 0 or you get 1 for doing the right thing. Questions like this are a little bit more nuanced because we're asking, okay, you have to sort of, you know, it's not a binary choice, right? It's not like, if we limit it just to 1, it actually is like this, kind of, more or less, right? So usually here it's more than 1. Otherwise, you know, there is not much difference. There is slight difference because here you cannot tick a second one wrong. Here you kind of can, right? Yeah?
My question is are the answers also nuanced? Like the actual facts?
No, the answers, I mean, it's clearly 2 are correct, 2 are incorrect. I mean,
okay,
you know, it's not that nuanced that Oh yeah, maybe it is, maybe not. No, no,
No,
no.
but like half the statement is like, okay, that sort of makes sense, but
Yeah, and also for questions like this, there are two extreme cases, like 0 are correct and all are correct, and those are not used, right? So you have to tick at least one, but not all.
Well, you have no idea how many are correct.
No.
so if you have like 6 questions or 6 choices you could take,
Yeah.
And only 2 of them are correct,
Yeah.
could you distribute the 2 points over like the 6? So if you have ticked 4 of them,
Yeah.
and 2 of them are correct,
Yeah.
you would get a distribution over. So you have the 2 points split over the 4 somehow. I'm not sure of the.
Yeah, that's so you're basically suggesting
Yeah,
that as well,
basically
right?
that, but
So if I have 6 points and I only get 2 positive ones, for the 4 negative, I should add them up to -2. So then I end up with 0 if I mark everything, right?
No, but that's that's the case if you have only 4 questions, no 4 possible answers. But if you have 6 possible answers, then
Each one's worth 0.2.
yeah.
So marking 2 correct ones and 4 wrong ones will give you a minus 0.4.
I think I have the solution to that one, because I think you can take the number of the answers that you have correct divided by the number of answers you have given minus the number of answers you have wrong divided by the number of answers.
That's right. We can normalize it. Yes.
I would also like to limit it at 0 so that you get positive if you're trying, because I don't want to bet on my grade by thinking like, okay, I think I have the correct answer, but I'm not sure, so therefore I'm not going to answer. I want to be certain that if I'm trying my best, then I will get the best grade I can.
That's right. So that brings us back to this one.
Yeah.
Whereas by not answering, you're actually also being punished, right? So that's not an option. You have to answer.
I don't like that one. I want to have 0 as if I'm answering wrong on a given question. But I see this one, the second, multiple answers, I would see that as one unit of question, sort of one question.
Yeah, so I get the idea of you wanting to get 0 if you answered wrong, right? The problem here is that you can answer partially wrong, partially right, and very wrong, and just a little bit wrong, right? So just having for all of those cases 0 is a little bit, it feels not quite right. For this is fine. For this case, yeah, it's a little bit more nuanced, right?
It's still okay if we limit the worst answer to be 0. Like even if there is someone who gets 0, even though they have something that is slightly more correct, I would still say that that's okay as long as you can't get negative numbers on just answering questions.
Yeah, but how can you avoid getting a negative answer here?
You can get a negative answer and then you can offshift that to 0 if it's negative. You can say, okay, if this number is negative, then I'll say it's 0 instead.
Yeah,
That's
that is possible, yes.
It's a conditional check.
Yeah. All right, so think about it. We haven't decided yet. We will discuss it later, yeah?
So basically more like percent, how much percent you got right of the total answers is basically the same amount of percent you get off the possible points for that question.
Yeah.
If you're talking about mine, it wouldn't be percentage. It would rather be like precision, I think, or accuracy.
Yeah, it's an accuracy. Yeah, it's how big the boxes are, right? With this more granular one, the boxes are smaller. With this kind of a more coarse-grained, the boxes are binary, 0, 1, and they kind of add up, right? Here you get a little bit of more of a decimal precision of, okay, it's not quite 0, it's not quite 1, it's like 0.75, right?
Yeah. But, so you use like mathematics accuracy in calculation.
That's right, yeah. But it's kind of the same with this. basically we extend the range, basically, right? So what we are saying here, normally you have from 0 to 100, and you have 100 steps, right? Now we have 150 steps, right? We just then renormalize it from 0 to 100, but we are more precise. We have this extra decimal places between, in grading, right? So to me, that basically that's what it adds. Yes?
I think there's a very simple solution. At least I really prefer that each question defines how many answers are correct. And if you do that, then each correct answer can give you 1 point. And if you then choose to add another answer, then the additional answers could be like -1 for each answer. And then you could also do that if you don't answer at all, and there are supposed to be 2 answers, then you can get -2 points. So then you will solve both issues.
Yeah. So I'm fine with that. I kind of I understand the rationale. From our end, because we're substituting, like, and historically we had questions like, for example, list factors for something, right? Or what are the factors for something? And we don't have in a bracket, there are 4, right? We just ask you, list the factors. You have to know, how many to list. So by giving you the number, okay, how many are correct, we kind of changing the nature of the exam by doing that, right? So in the original exams where we were marking them, we ask questions like, okay, what are something, right? And then we don't tell you list 3. Sometimes we did. We say list 3 things, right? But sometimes it was kind of an open. And then you have to come up with how many you want to say. Here it's sort of similar, like there are some factors or something, and you say which ones are relevant, right? And the choice of which ones are relevant and how many is kind of part of the question. If we say which factors are relevant, and there are only 2 here which are relevant, yeah, that gives additional information which the original exam was not giving, right? In fact, in the original exam, you didn't have the choices. You have to come up with the 2 or 3 factors like from your head. Here, we just list them, right? So it's actually much easier to do that with the list, which is already there, than without the list at all. So then even saying, oh, here is the list, and only 2 are correct, right? We're making it so much easier for people to do the question compared to the original question, which was list the factors, right?
Yeah, well, if you give that kind of questions, then I understand.
Yeah. So, yeah, I think, yeah, I kind of understand your concerns. I understand some of the connotations of doing the negative points for negative things, and or between carrying over the negative points between the questions, right? That has been discussed before as well. So yeah, anyway, we will kind of come up with something and then go through this with you before the exam happens. There is one extra thing. Yeah, it is a little bit of an experiment of having an exam completely marked by a computer, right? So we are, oh boy. We have some questions such as that.
Review it. The computer will mark, but the computer doesn't have the authority to, give the mark.
Yeah, that's right. I mean, we have to go over it afterwards anyway. What we are planning to do is we're planning to have textual questions where you have to type in a word. Have you had those with Inspera before? So there is a sentence saying blah, 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 and then you have to type in the word and blah, 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 right? And this word is the answer to the question. Yeah, 1 point if you got the word right.
Please do not have several of those in the same question. I remember some examples brought up from the data communications exam.
Yeah.
Where there was what is blank in blank with what considering blank.
Okay, it will be not as bad.
Yeah.
Yeah.
And also hopefully check those.
Oh no, you had a space. You had a capital letter. Well, that's the wrong answer. No.
Yeah, exactly.
That's something we need to keep an
So, I mean, we're doing it, again, a little bit as an experiment, checking how much the computer will get it right and how much we will have to go after and do the remarking manually because, yeah, the computer kind of gets, or we get it, because we have to list all the alternatives, all the variations of plural and whatever, right, for the computer to be able to do it.
Yeah, you have a typo.
Yeah, exactly. Like, if you have a typo, the computer say it's 0, right? But, like, okay, for typo, you don't get 0, you get 1. I mean, it's just a typo, right? Doesn't matter. And we cannot remove this possibility. So, first of all, make sure you don't have typos here. Second of all, don't use weird characters. Just use, you know, space and.
Oh, sorry if I'm unsure how to spell it. I'll just Google it.
Yeah.
Yeah, don't worry.
But we will. I mean, we are doing an experiment for ourselves. How much work is that? Because if we have to mark most of you anyway, because most of the things computer get wrong, then, you know, yeah.
Well, if you have that in there and you're not sure that it will always be correct, which it doesn't sound like you're sure it will always be correct, then you have to go over all of them and check.
No, I mean, if you got, like, if there is a question and the total score for it is, like, you know, 4, and you get 4, we don't have to check it. We only have to check it if you get less, right? Yeah. So hopefully that means some people will get it right. If nobody got it right, yes, then we have to check it for everybody. All right, so back to the lecture. Today's lecture is about P2P. What's P2P?
Peer-to-peer.
Okay, what's peer-to-peer?
Sending information directly between clients instead of going via a server.
Good, good. So what's BitTorrent?
What?
What?
No, I'm kidding. You download.
How BitTorrent works? Who knows how BitTorrent works? Who uses BitTorrent?
I used it a lot more before.
Yeah. So how does it work?
You transmit data. Sorry. Go ahead. Sorry. You transmit data directly between other BitTorrent clients instead of going via servers. You share files by having some of the pieces, and whenever somebody else joins, so you have another pair to send data to. Yeah. Everyone shares whatever pieces they have, and you have usually at least one server sending out the entirety of the file, so that, you know, all the pieces will be available eventually.
Right, exactly. So how do I know which piece is which?
I'm going to go out on a limb here and say hashing, since it's on the, the slide.
Very clever. Good. So we have a couple of core concepts here, right? So we have a concept of a swarm, like peers, which can communicate with each other, right? We don't really have a central server. We can share information directly between peers, right? The other concept is we have some sort of a file. So, you know, imagine that we have some sort of large file. It has been cut into chunks. Chunk 1, 2, 3, 4, 5, and then the nodes have some chunks. Let's say this guy has chunk 1 and 4, and this one has 4 and 5, and so on. And then they say, okay, I need chunk 2. This guy has chunk 2, so it says, okay, I can give you chunk 2 here, and the chunks are hashed. So we kind of address them by content, so we know, okay, I don't really know what it is. I know it's the same hash, which means it's the same binary sequence of bytes. So off you go, right? Great. So how Git works? What's Git?
I like referring to commits, like checking if the two files are equal by hashing them and seeing, well, did they change? Well, hash them again and see if the hash is different.
No, it's yes, almost. You're not hashing files. You're hashing the changes between the files.
Right.
Right? So the notion that the big innovation of Git was that we don't care about the actual file, like with SVN and so on. We just care about the change sets which happened on top of the original file, right? And then we can apply those changes to get to the version that we need to get to. And then we can play with those changes and reorder them and combine them and do different things with the changes, right? So Git doesn't really track the versions of the file. Git tracks the changes which happened to the file, right? And it allows it to do magical things, right? So in a sense, if you had the same applied here, and you have kind of let's say you have a movie, and from 1 minute 10 seconds, for 10 seconds, you play a video clip in that movie, right? The hash of that video clip would be the same as the video clip alone, right? Although this is a different file and this is a different file, right? But the hash is the same. So therefore, I can get that piece from another file, which happens to be exactly the same, right? I don't need to get it for this file. I can get it from another file, right? So Git does that, right? And also with Git, sometimes it's a little bit interesting because two people may make the same change independently of each other, or you might make the same change independently of each other, right? Of yourself, not each other. So then Git will kind of know that. So then Git will know that actually this is the same as this, so maybe that happened in the past. And then sometimes you get some weird behavior because it reorders the changes in such a way that's like, no, I was reverting the previous change, but it's like, no, it's the same change, right? So you can kind of get some interesting workflows. And all of it is because of hashing. So what is hashing? Yeah?
It's a function that takes an arbitrary input of length input and then gets an output that is of set length.
Mm-hmm.
So if you get different inputs, then you will always get the same output length, but they should be different. If you get the same input multiple times, then you will always get the same output. You're trying to remove hash conflicts, so the function should try to use like prime numbers and such, so that there is a long sequence of different outputs that can be given from similar inputs that are not the same.
Yeah. Yeah. This is correct. There is like a small small nuance. So I have inputs of different length. So variable length, and the input of variable length, long or short, goes through the function, and then at the end of the function I have something of fixed length, but that can be quite short. I can have a fixed length of 2, right? So if I try to hash different text, I try to hash my emails into a hash function which gives me output of length 2, I will have collisions, right? So what the hash collision is that I have a document 1 and document 2 going into a function and resulting in result 1, which is the same for those two, right? What we try to do is we try to keep this large enough that this doesn't happen often. But you will always have hash collisions, no matter what you do, because the domain here and the domain here are such that this one is much larger than this one, right? We're trying to keep this big enough that the likelihood of the collision happening is so small that we can ignore it, but it will always happen, right? So collisions are inevitable, they will always happen, but what do we want about the collisions? What is the property that we do use the prime numbers for and all those things, not to remove the collisions, but what to achieve? Yeah?
That the input should be quite different for the complex, for instance.
Yes.
So if your function, for instance, is just take the two first bits and then output that into the
yeah. So that's one property. So one property is the sensitivity. Very small variation in my input results in a huge variation in the output, right? So that's one property. What's the other one? They are related somewhat. Yeah.
The other property I think is that there's a long cycle, so that every output is generated, or like it's no output should be left out. So few of them should be.
Yeah. So that number 0, let's say. That's about the use of the space. We want the space to be uniformly used up such that it's hard to do cryptanalysis on the space, right? So we don't say, oh yeah, there is a subspace of that domain which is kind of more frequently used, therefore we can focus our hacking attacks or something on that subspace. It should be kind of uniformly used up. So this is kind of about the properties for the cryptanalysis. But what else? What I'm looking for here? That property I'm talking about here is that given D1 and hashing it to R1, it's very hard for me to find D2 which hashes to R1 as well. So the ability for me to guess D2 which hashes to that is super hard. It's computationally like impossible. Like there is no algorithm for me to be able to do that. I basically would have to do a brute force search, right? If I'm forced to do brute force search, that's best, right? If I don't have to brute force, but I can somehow constrain the search space, but it's still very big, yeah, that's good enough. But if this is easy, if it's easy for me to put a lot of computers and crack it, then that hash function is crap, right? Because I can generate the collisions like at will, right? So the inability to generate the collision is the property that the good hashing functions have. And what happens? Like, we have a hashing function, we use it for a while, and then what happens? Yeah?
Computers get good enough that they can just crack it.
Yes, with some hashing functions, we got, like with MD5, we got to a point where, yeah, it's like feasible to brute force it, especially if you're doing some short passwords, short sequences, right? But what else happens? Well, scientists kind of discovered that, well, this space is not as uniform as we thought. There are some properties which we can exploit. And they use those properties to come up with ways of restricting the search space in such a way that they can force the collision, right? And that happened 2 years ago with SHA-1. And then like the hashing algorithm Git is using is actually vulnerable for people to forcing the collisions, right? What does it mean for Git? Well, it means for Git that I can send you a patch which will have the particular hash, and then it's signed by, let's say, Microsoft, and then the patch itself is not what the Microsoft has, it's the patch which I want for you to patch your system with, but it's already been signed with some vendor, right? So I can technically generate a patch which has the same hash to what the original patch had, but it's different, it's actually doing something else. How likely is it to happen? Very unlikely, and it's still very hard to do those collisions, right? The demonstration which Google did, they used up all the machinery that they had. Like, you cannot really easily do that. So, Git said, oh yeah, okay, it's a vulnerability, but we can, ignore it for a while. But it's sort of, it happens from time to time. From time to time, something is discovered about the space that we're dealing with, and then you have to switch to a better, longer or harder hashing algorithm. Okay, so let's change the gears a little bit and let's think about creative work. So let's say you've painted a painting, or you came up with a poem, or you wrote a you know, a short novel, right? Or you painted the Mona Lisa, right? Have you seen Mona Lisa, the painting? You know, a guy back in the day painted it, and everybody in the world seen it, right? So how it happens that those things stay in the world? Like, who is paying for Mona Lisa to be around? How does it happen that this creative work kind of stays in the world?
Well, some people conceive it to have value, so they preserve it.
Yeah.
Do you mean stay or producing?
Stay. So how, let's say you've made a painting, right? You've painted something. It's on a piece of paper, right? And I'm not talking about this piece of paper in itself. I'm talking about the depiction of what's in there. So if someone takes a photo of it and this disappears, I still consider it will stay in the world because it's kind of copied, right? So how things stay in the world for a long time. So one argument is that, okay, some people see value in it, so they preserve it. So, you know, someone wrote a newspaper article, and this newspaper article was published by, I don't know, Jobbik newspaper, right? And then this newspaper is archived because Jobbik Kommuna thinks archiving all the newspapers is good for the community, so they're archiving it, and they taking, you know, photographs of it on some fish, you know, storage or something, and then you have it stored in the world for 50 years or 100 years, right? That's one mechanism. What else? Yeah?
It's spread to so many places on the internet. Say you're I don't know, when something is, I don't know, I guess popular for a little while, it's spread to a lot of places in the world, a lot of servers, and a lot
Yep.
of those don't go down. And a lot
That's
of
right.
those
So here I'm trying to avoid the internet. We're not talking about the internet things. We're talking about like artifacts, which are more physical. But you know, something becomes popular. You know, Mona Lisa as a painting became popular. A lot of photographs has been taken of it. It has been reproduced in a lot of paper reprints and all those things. And it kind of persists in the world, right? Will Mona Lisa be known in like 100 years? Yes, I think so. In 1,000 years? Maybe. In 10,000 years? Well, maybe not. I mean, I'm not sure what people painted, you know, 1,000 years ago. Some paintings are around, and we have some, you know, cave paintings around, but some things disappeared from the world, right? So things persist, but some things disappear. And one mechanism is that those popular things persist, and the less popular things kind of disappear, right? But it just happens, right? Like nobody is necessarily controlling it or scheduling it or paying for it. It's sort of people do it based on the demands or based on the you know, the dynamics of life, right? Okay, so when we move to the digital, you know, how is Linux being around? Do you think if Ubuntu and Fedora and all those companies which do Linux went bankrupt, they just disappear, they got busted, would Linux disappear from the world?
no,
No. Why? Why not?
because it's in so many places and so beneficial for so many
People?
companies to use them. So
That's right.
they would keep maintaining them even if somebody stopped.
I agree, exactly. So how about like a tic-tac-toe game? Same, right? Somebody came up with the game, and now it's kind of known. Like you pass it to your kids, and they know it, and they pass to their kids, and they know it, right? Is somebody paying for it? Is somebody taking royalties for that?
I hope not.
I don't think so. So there are some things which kind of persist in the world just because of the nature of the world, right? And with Linux, it's the same. I mean, Linux was around before the companies were set up to push it, right? It has been originally an open source project, which was sort of distributed by people between themselves, and it was around in the world without additional structure, right? So, well, so if you think about it, let's say you're doing a piece of software, and now this piece of software is used by somebody else's. piece of software. So you have a dependency, right? You have a dependency tree. What do you normally do with your dependencies? So what happens with dependencies? Where are you getting your dependencies from? So you set up your Android project. You need to use a JSON library. Where you get this library from? The internet, but where exactly from?
Servers.
Some sort of repository, some server, right?
Yeah.
And that server is maintained by somebody or by something, right? And it's being paid by that group of people or whoever is maintaining it, right? So let's say there is a particular dependency that you need. So you say, I have to get it from this Maven repository. This Maven repository is managed by some institution, by some organization. They pay for the bandwidth. They allow you to access it, and they get their revenue somehow, right? If they get bust, if they get broke, where you will get this dependency from? Well, from another repository. But if all the repositories go bust, where you will get the dependency from? Well, you will ask your friends, do you have this jar file? They may say, yeah, I have it. Okay, can I get it, right? So even if all the repositories go bust, all those dependencies which are around will not disappear suddenly. They will be spread all around on people's computers. Developers are still using them. They need them. You need the JSON library to parse stuff, right? So how all of that was working before the internet?
Floppy disks.
Yeah, it was kind of complicated, but you had floppy disks, you had friends, and you were moving things around manually, right? Yeah.
Search engines for jar files, right? Things like that. So they would just, index pages based on jar files they found. You would, I forgot the. Nowadays you can use Google anyway, but.
Yeah, but that already presupposes internet, right?
Of course.
Yeah. So before internet, things were around, dependencies were around. You get your, I needed a particular library. So I went to the school every Saturday. At the school, we had the fair. We were meeting on a giant, soccer field. And you just walk around and you ask, do you have that? Yes, I have. Great. Can I copy it? Yes, you can, right?
Going around with
You
you
go
stuff.
to the literal library and ask if they have a certain library.
Yeah.
And that's amazing.
Okay, so now comes internet, comes technology which allows us to store things and retrieve things much easier than in the old days. We have those repositories, but would it be nice to have a mechanism which allows us to, for example, publish something in such a way that it's not controlled by anybody, and in a sense that it's available as long as it's popular and people use it, basically for free. So nobody needs to maintain the infrastructure for it, right? Piggybacking on the existing internet infrastructure. Would that kind of be nice, for example, for dependency management?
It would be nice, yes.
Yeah.
But someone has to run the servers.
No?
Yeah, they do.
No? I have this dependency and you need it. And because I have it, I run the node from which you can get it, right? And when you copied it, you now part of the peer-to-peer system which hosts it. So if Christopher needs it, he can get it either from me or from you.
Everyone is maintaining it, so the sentence stating that no one is maintaining it is false. Everyone is maintaining it.
That's right.
Everyone says they're
Correct. Yes.
Yeah.
Yep.
So how would you then go and update the library?
No, you don't. It's immutable. I mean, why would you update the library? If I have a library version 1.0.0, that's it. That should never change. It should have the same hash, for life, right? If you need to update it, you release 1.0.1.
Well, you can search the network, right, for new version.
Yeah.
And if someone has a new version, then you could connect to that pair and ask, well, hi, you have some packages that I really want. Can you send me those?
That's right. So what we can do is we have an original library, which is 01.0, 1.0.0. It has a particular hash, hash 1.0.0. And, people can get it, right? Can search for it and get it. Like if there is an update, you have a new library, which is 1.0.1, and it has a new hash. And then you can find it by the hash. And here you can find it by the hash. It has a unique hash which identifies that piece of software uniquely in the world of all the software, right? And then we don't have the infrastructure, we don't have servers storing it, everybody's maintaining it. So everybody is in charge of whoever is using it. If the particular library becomes obsolete and nobody is using it, it just disappears from the world, right? If nobody wants to keep it on the computer, if I don't want to keep it on my laptop, then I don't. And then if all the people in the world decide not to keep it on their laptops, then it's gone. It's, it doesn't exist anymore, right? But if people keeping something on their laptops, it persists, right? Would that work?
It would be practical because everyone have to use their CPU time to host everyone else's file sharing.
Not necessarily.
Oh.
You can restrict it to only host, like if you are part of this, if you are part of this network and you have your computer, right? And you're developing for Android and you have, I don't know, let's say 10 libraries, right? So you have times 10 of those libraries on your laptop, then you already have them on your laptop and you don't store anybody else's stuff. But you let other people to get one of those 10 things that you already have on your laptop. So there is a cost for the bandwidth, for you sharing it, but not necessary for the storing.
Well, when you're downloading a dependency, that means 150 other people has to send you packages that you need, and that requires their CPU time and all the resources.
So,
right?
So you have another developer who needs your library.
Yes.
Right?
Yes.
You have to send him that library, but you already have it on your laptop. So you only have to pay for the bandwidth that he's using from your laptop. But storage-wise, you don't pay. Yeah. So yes, there is a cost. You know, everybody personally has to take the cost. And also, if he has a library which you need, you don't have it, then you have to download it and store it in the system, right? So there is some storage that you maintain, but you maintain it for selfish reasons. You maintain it because you need it. And then you spend some money letting people download it, but also you expect other people to let them download stuff that you need. So it's kind of a reciprocal, right? So would that work? What do you think?
Would this be like what you are talking about now? Like, is this proposed to be like for the entire internet or for major parts?
Yeah, it is for the entire internet, unfortunately, yes.
Yeah,
so I mean, the picture I'm painting is somewhat in between, right? I will tell you what's already there and what it could be if you modify it somewhat a little bit, right? So there is a system which is called GX, and it basically does what I just described. It's a dependency management system for all sorts of different languages that you want. It's written in Go, and it manages dependencies in such a way that they are persistent, immutable, and not stored in any of the repositories. They are stored in the participating peers, which are participating in the system. It is using a particular technology. Okay, so tada, we kind of into the underlying technology for the GX system. So what is this? Unfortunately, I didn't share the slides because my goal was for you to Google it and come up with what it is, right? But I will have to do it like instead of you because I didn't share the slides, and I cannot expect you. Whoops! I cannot expect you to copy and paste. Yeah, to type it, right? So I will copy and paste it.
I expect it to be a hash that identifies a certain dependency you can download.
Yes, so it is a hash of a file which is stored in this distributed file system, which allows you to access resources that you don't locally have, but you can download or share, right? So the system is it is a peer-to-peer system. You run a client, and then you're part of the swarm of the network. And then you can use this swarm to download things that you don't have, and you can allow other people to download stuff that you have, right? So it's a combination of Git and BitTorrent in the kind of a single system, right? The objects which you're storing are immutable. The files that you have cannot be modified because then they will have a different hash, and that becomes a different file, right? So every modification to a file you're doing creates a different object in the object space. There are systems, so to run it, you have to have a daemon running on your machine, which allows you to interact with the system. The system is called IPFS, and there are web gateways which allow you to interact with that world of the file system, distributed file system, via the web interface. And one is called hardbin.io, I think. IPFS, and then if I pass this, no, so it might be com. Yes, and here we go, right? So I just use the web gateway to connect to the IPFS file system to retrieve that file and display it. It's a text file, which is a quick start to the IPFS system itself, and you can sort of follow the the tutorial. It's kind of a quick start guide to IPFS, right? So before we go into IPFS, I forgot I had one extra slide. So how about Google Drive that no one owns? Exactly, and that's exactly what IPFS is, right? It's a global file storage which is provided by the participants, and it's basically it's free in a sense that you don't have to pay anybody, but you have to pay by dedicating some resources for other people to use it, as other people are allowing you to use it, right? Okay, so how about Amazon Cloud-like system which no one owns? So not only for storing things, but only for running things. So let's say you came up with here you came up with a dependency, right? You came up with some piece of software which other people can use, and it's let's say it's a jar file for Android, right? Now you can publish it using the IPFS, and as long as people are using it, it will persist in the world for free. You don't need to pay for hosting it anywhere. You don't have to pay for bandwidth anybody. You don't have to host it yourself on your own laptop neither, because as soon as other people are using it, they will be hosting it, right? So once you release this dependency into the world, it will persist for as long as somebody is using it. If nobody is using it, it will die, right?
Well, you host it yourself until it is self-sustaining.
That's right, exactly. Yes, exactly. Or you can basically host it yourself forever, right? But how about instead of you developing a jar file, you came up with some clever Go service that does something. Let's say, for the sake of argument, you're converting between Celsius and Fahrenheit, okay? It's a service. You get a Celsius, you spit out Fahrenheit. You get Fahrenheit, you spit out Celsius, right? It's a service. You don't want to host it. You don't want to pay nobody for hosting it. You don't want to set up an Amazon account for hosting it, but you want people to use it, right? How would you do that? Well, we need something like this. We need something like Amazon Cloud, which allows you to deploy something that does some logic, but then nobody is owning it, right? It has similar properties to what we just discussed for the IPFS, right? Is this possible? What do you think? Does this exist? So this one I already spilled the surprise, because I already told you that this one exists and how it works. How about this one? Okay, I mean the disclaimer kind of hints that it sort of exists, but not quite yet. Yeah.
You mean that it is run on several computers at the same time, or only on one computer at any given time?
Well, I'm thinking more like, let's say you have kind of like Amazon-like platform, okay? How Amazon platform works? It works on, on a cloud, on different computers, right? But it is sort of conceptually, it's like a computer which you can deploy your stuff into and run, right? But you have to pay for it, and they have to maintain it, the Amazon people, right? So I'm thinking about something like that, that it is something on the internet that basically allows you to deploy code which will run forever, potentially, without you paying for it personally, and it will be sort of maintained by this peer-to-peer network. Yeah?
I think you could modify the blockchain.
Yeah.
Smart contract.
Yeah, that's right. Very good. Yeah.
I mean, there has been, if you go to games, that you have, in multiplayer game, you have one person in the lobby, which is the host.
Yes.
And as soon as it leaves, it will migrate to another person in that lobby who will then turn into a host.
That's right.
So the idea behind it already exists.
That's right.
So it might exist already.
Yeah, exactly. So both answers are good. We do have systems which are prototyping it, which are using the blockchain technology. But there is a disclaimer. We haven't worked out all the details yet, right? Both technologically and monetization wise, right? So who would use it? I mean, everybody potentially could use it, but who would pay for it and how? That's how we're working it out still. Also, some of the properties of the system still under kind of a heavy development. All right, so IPFS. I will not play the videos. If you go to ipfs.io, they have two main videos there. One is like 1 hour long, so it's quite lengthy, but that one is better. And then there is a demo video, which is 8 minutes long. And I encourage you to watch at least the 8 minutes, okay? So have a look at IPFS and how it works and how you can set up your client and how can you use the GX dependency manager. It's quite popular with some of the Go projects. I've already noticed some of the GitHub Go projects use GX as an actual dependency manager for themselves. And yeah, there are some public gateways for IPFS, so you don't need to install the client yourself. You can browse the file system by going through some of the public gateways for the IPFS. And I stress that IPFS, it's sort of like a global Google Drive for immutable files that no one really owns, which will persist as long as somebody else is keen for having them hosted, right? Which leads to some interesting ethical challenges, because if you have an illegal document and you put it into the IPFS, how would you delete it? Well, technically it's not deletable because as soon as some other peers are having it, it's like spread all over the world, and then you will not know, who to contact to delete it, right? It's a very tedious process.
I mean, you could, like if you have an automated system for that.
Yeah, but there is no automated system for that.
No, you could send out like a kill order to everyone, and whenever they receive a kill order, they send it to all of their pairs, and whenever.
That's right. But then the problem is with the censorship, right? Yeah. Currently, the system is sort of censorship resistant, and that's why they don't have all those features in. How you balance that, right? Okay, so that was about the Google Drive. Now we're talking about Amazon. So before we go to the main topic, 3 questions. So why was Bitcoin invented?
Moral issues.
Yeah. What else?
Moral issues. And, cool technology. Those are my
Yeah.
Bitcoin for trying to get away from the dollar as a standard, trying to move it to something that you can actually trust.
Yeah, something that is not controlled by the state services, so to speak, right? So dollar is a currency, for example, which is controlled by the central bank of US and they can manipulate it by increasing or decreasing interest rates and so on and so forth, right? And they also can print more of it if they want to, which in the past they've always done around the war times and so on, right? If you need more money, just print more money, and they buy weapons, and then we will think what to do with it, right? So what is it for? Well, it's a kind of a solution to the consensus problem, right? So Bitcoin is technically interesting because it solves a distributed computing consensus problem by aligning the incentives of the people who participate with the value of the tokens that are involved in the system itself. And do you know how it works, more or less? Yeah?
I have a good idea of it, but I don't know the details. But I know it's very safe because you can't just invent more bitcoins. Because everyone that has a Bitcoin wallet is bookkeeping everyone else's Bitcoin wallets.
That's right.
So faking something and trying to print money, you would have to take over 50% of all the hosts.
Well, it's impossible. Yeah.
It's possible technically, but no, we can't.
Not practically possible. So it's relatively safe. The transactions are public. All the transactions between people's wallets are publicly visible. They are really hard to fake. The identities of the wallet owners are hard to track, but it's possible, so it's not truly anonymous. And then inventing new bitcoins, yeah, that's really rather impossible. And it has kind of a three main components. So it has the users, it has the kind of infrastructure providers like wallets and so on, so kind of a software developers, and it has the miners. And the miners are the ones who kind of do this problem solving and coming up with the hashes of certain difficulty that identify particular transaction blocks, broadly speaking. So we will not go into details, but basically how it works is that you have kind of a hard computational problem that you have to spend a lot of computational power and around 10 minutes to solve. And once you've done it, you will get a little bit of a reward. And then you don't want to fake it because then the reward will be taken away. So when you've done it, you really want it to kind of persist. So you want it to be done correctly. And then the system kind of perpetuates itself, and those blocks kind of reference each other. And the longer the chain you have, the more trust you have that the transactions included in the previous blocks are kind of correct. All right, so let's have a short break, and then we will talk. We will not talk more about the blockchain. We will talk a little bit more about Ethereum and the smart contracts and how we can do this kind of computing in this global computer. So 1:30, we resume the lecture. Okay. So before we do this, small logistic announcement. Come on. Okay, so I ran a Google query. Maybe I can get it without the 1.5 meter.
Or someone advertising for an app that has better accuracy than the technology allows?
Yes.
Cool.
Cool, nice.
So yeah, I have to put 1.5 meter to get the link I want. So there is an app called Live Roads. You probably can just Google for Live Roads. So the Live Roads is an app running on Android, and it promises to give you up to 1.5 meter GPS accuracy, right? On your phone, on your standard phone with no additional attachments. So now the question is it possible? So let's say your GPS, let's say your GPS gives you 5 meter accuracy, okay? That's the fact, okay? Okay, let's say it's really good and it gives you 4, okay? What cannot you do with 4 meter accuracy from your GPS when you're driving a car?
So what can't you do?
What you cannot do. So when you're navigating with your normal GPS app like Google Maps, what it cannot do, yeah?
Which side of the road you are?
Exactly. It cannot tell which side of the road you are and which lane you are on, right? So if you're going on a 3-lane road, it knows, well, you're on the road, most likely, but which lane, well, that's too hard to say, right? If you have 1.5 meter accuracy, then you can, with quite good precision, tell on which lane you are in a car, which is very helpful when you have a navigation app, right? So now you have this company promises 1.5 accuracy, right? And high definition maps with lanes, and will be able to tell you which lane you are on the road on your Android device. Okay, so there is a question. I can't figure out how it is possible. The question to you is it possible?
Using the current GPS technology alone, no?
Is it only using the GPS or is it using the direction that you're traveling in?
Yes, it uses the direction as well.
Okay, then I guess it's possible.
Yes, so it is possible to improve on the accuracy of the GPS by taking into account other factors which are, are pertinent to what you're doing, right? So I will not give you the full lecture on this. I put a link for those of you who are interested on learning more. The link is tutorials, Kalman filter tutorial. So you can read the tutorial. But for the sake of the arguments, what we want is we have, I just give you kind of a basic concept very quickly. So we have a car, let's say, on the road the car is traveling with this direction with a particular speed. Let's say you're doing 60 kilometers per hour, right? And we are getting a GPS location of where you are in time t with certain error, right? So let's say I'm getting the location of where you are with certain error. And I know you're kind of roughly somewhere here, but that's t0, right? And I don't know exactly where you are because I have the GPS error, right? Now I know for sure your speed, right? Again, with some error because I know the speed from the GPS measurements, right? So even though the GPS kind of jumps a little bit, I kind of know what your speed is, probably more accurately of where you are, right? So the accuracy of the speed has an error as well, but this error is probably smaller than the location error, right? So now I have this. What else do I have? I have the accelerometer data, and I have the gyroscope data, what is happening with the car, right? So I'm using your speed, the direction of your movement, and the accelerometer data and the gyro. Now, can I predict of where you will be in time t.1, not using GPS, but using all the other information that I have, right? Well, I can, because I have the normal laws of physics. So if the GPS says you're here, and you're moving with that speed, this direction, I can predict, okay, in time t1, you will be here, right? With some error that I have around this calculation based on the errors of the other data, right? Now, I actually predicted that. I moved with the car. I'm now here in time t.1. It is t1. And now I'm getting the new GPS estimates of where I am. So the GPS tells me, okay, you're kind of here. My prediction was here. And I'm kind of doing it forever, right? So I'm kind of knowing what is that difference between where I was predicting to be and where the GPS tells me to be versus all the other sensors that I'm using. And I'm kind of getting more and more confident of what that might be. I'm getting kind of a narrow bands of all the errors that I'm getting, but because I'm doing it recursively all the time when the time passes, right? As the time progresses, I'm getting quite good at it. In fact, I'm getting so good at it that I'm better than the GPS alone, right? Because all the other metrics are kind of relatively solid. They give me the very accurate, you know, if I have my phone in the car, the phone knows very precisely what orientation the car is in, right? The error of that orientation is so much smaller than the error of the GPS that it's very useful to use in estimates. The problem with this is that it drifts, right? So those metrics which I'm getting from the phone, they're quite accurate, but in time, the small errors accumulate and they tend to drift off, right? So my perception of where the phone was pointing initially and after an hour might be different. But with the GPS always correcting it, I'm kind of getting being corrected to the proper path, right? So a Kalman filter is a mechanism of statistically analyzing the data that I'm using here to get a more and more accurate predictions and calculations of where I am based on the prediction together with the GPS report. And then I can say, okay, with a certain error, certain probability, you're exactly here, right? Based on the data that I'm getting. You understood that? And this process of combining different sensors for something that you want to achieve is called sensor fusion. And we do that for augmented reality, for virtual reality, for navigation, for drones control. We do use it for various systems where we have multiple of sensors, but we want a very high accuracy of something that is not achievable by any of those sensors alone, especially the GPS, right? So for example, when we were discussing in the past the variometers, which tell me how high I am, what is the altitude of where I am, right? So of course you can use GPS for that, but that's not very accurate. You can use pressure, which is much more accurate, right? And I can combine both pressure and GPS to get even more accurate estimates of what is happening with my altitudes, with my coordinates in the altitude level by combining the two sensors, doing a sensor fusion and using a Kalman filter to achieve the calculations.
Wouldn't you be better off just using the more accurate sensor?
No.
Rather than combining inaccurate measurements from the other one?
No. You would be better off combining the inaccurate measurements from both than using the more accurate one. Because the more accurate one, what is happening is with the more accurate one, so think about it like this. You have the location given to you by a more accurate sensor, which has a certain error, okay? And then you have a location given to you by a less accurate sensor, which has a larger error, okay? And you have, let's say, another sensor, which gives you yet another location, and it has an error which is sort of bigger than this, but smaller than this. Now, where I'm truly at. What is my true location? Am I truly here by the more accurate sensor? No, you're probably somewhere here, right? If you think about it, you have 3 sensors, 3 different location estimates with 3 different errors, and now you have to estimate where you really are. Well, you see the less accurate, the 2 less accurates are skewed a little bit towards the southeast, right? Which means the more accurate one probably is not giving you the true position. It's sort of skewed because you probably should be a little bit more southeast because the way the errors compound, right? Yeah.
So basically, it takes the weighted average based on all the sensors.
Based on their accuracy.
Yeah.
Yes.
A weighted average.
Yes, that would be inaccurate, but you have to take into account the time domain as well. So it's not an average, it's not a weighted average in T1, it's the weighted average of what I've learned so far about the error drifts from the past, which I was doing it forever. Yeah, exactly. Then that's what it's happening. And that's what Kalman filter actually does. Great. So that's one thing which I forgot. The other thing is there was a question yesterday about the marking schedules. Like students are always interested, like how we come up with your marks for you, right? So roughly speaking, we have discussed it that roughly speaking it will be like 40% is the exam. So we will discuss the exam later. 60% is the portfolio. The portfolio is split into 3 parts. The first part is the 2 first labs, and then the second part is 2 labs, and then the third part is the project plus presentation. The first 2 labs are 5 points each, roughly speaking. The second are 10 points each, and then the presentation with the project is 30 points. So the labs are roughly half of the portfolio, and then this is another half of the portfolio. Those are pass-fail, so you either get 0 or 5, you either get 0 or 10, and then here you will get something like 5 points for the presentation and 25 for the actual project, right? Yep.
So are the lab 1 and 3 on the first part? Or is it 1, 2, 3, 4? Because I would definitely say that lab 2 is worth a lot more than lab 3.
Yeah, that's a valid point. We could reorder it. What do you think? Are you all agree with that? That it's 1 and 3 and 2 and 4. So the even ones are more expensive and the odd ones are cheaper. Yeah, fine. Good.
But there will be no sort of extra points given for extra efforts in this.
They might be, but it's like not part of the picture. Yeah. And also I'm stressing that there is a presentation element, and we probably will run the presentations on the 3rd of May on Thursday, because we have quite a number of projects, so we wouldn't fit everybody on Friday. And if you have presentation on Thursday, you still can do some changes to the project before you have to submit it, right? So it's actually good to have presentations on Thursday. You don't have to have the project finished then, you just present it. How you present it is a show and tell. So you show how the screens work, how the game or app works, and then you talk a little bit about the development, like, how many people are working on it, who was working on which bits, and what was hard, what was easy, right? So it's kind of a show and tell with a little bit of details. Not very long, 10 minutes, maybe 15, depending how many features you have to demo, right, in the project. Yep. Yep. You.
Oh, that was me. Is there? I mean, how professional should it be? I mean, it should be obviously be professional, but should it be like, well, we have prepared amazing PowerPoint slide and we have a perfect schedule for the presentation, or should it be just, hi, we made this and we did it this way?
Yeah, so it ranges. If you can do the hi, we are here to talk about it in like 10 minutes, and it's like don't have awkward poses for a long time, it's fine. Most groups have some slides and like a live demo. So you plug in the phone with the screen sharing, and you show the others like how it works. You don't have to have very formal, like, of course, it's just for the class. So a couple of slides might be useful because it kind of keeps you on track. You don't go off tangent on a day. But some groups last year, they were doing it sort of live, and it worked okay. If you have some sort of schedule of what you need to talk about and how, like, who is talking about what, right? If you just completely show up from fresh, it may not work. So, yeah. Any other questions? Okay. So, we're back to the class. This is a big topic. I have like, gazillion slides about it, about 50. I have not much time. I'm trying to communicate the basic ideas about what it is and how you use it and what is currently capable of. So I will kind of run a little bit fast. So the details are not that important, right? To play with Ethereum, you need some prerequisites. You need to get the wallet, and you need to have the node, which is forming the swarm part of the network, right? So you have to be connected to the network. And then to actually play with the smart contracts, you have to have a compiler. You can use a command line compiler, but then you the workflow is a little bit easier if you use like IDE. It's a browser-based. It's not super fancy, but it gives you some warnings and some hints of what you're doing wrong. With you using a command line compiler, is like, with GCC or with typical, Java C compiler, it will tell you warnings, but sometimes it's a little bit hard to see how to fix it because it's out of context. So it's better to have an IDE. And then there is a main network. Actually, Ethereum has two networks. It's the Ethereum Classic and Ethereum Foundation. They split at some point. And there is a number of testnets which you can use. Some testnets are closed, so you cannot mine the test ether. You have to use the faucets. But there is one which is still open, and you can mine the currency that you need. Or you can set up your own if you want to as well. So you can have like a test environment just for developing on your own laptop. Okay, so yeah, this new versus old. It's a little bit of what we discussed in the past. Like historically, internet was sort of a kind of managed by enthusiasts, and everything was sort of open. Then we had the era of those big companies kind of taking more and more ownership. In the old days, everybody was running almost their own SMTP server. Like email was a very distributed sort of setup. Nowadays, email is very centralized. I mean, you have a couple of providers. Yeah, universities, they run their own. But a lot of universities even, they migrate to Microsoft or to Google for mail support, right? So it became kind of centralized. And you see that with other services as well, that they became centralized. So you know, being centralized, it's not very open. It's kind of dictated by whoever owns the central repository. So the new ways of doing things is more open, more sort of diverse, persistent. So as we were saying, like if you put something into IPFS, it potentially is there forever. If you put something on Amazon Cloud, it will be there until you stop paying the bills, and then it disappears, right? And then permissionless is that a lot of those systems don't require any sort of permission for you to be participating. You can participate by the fact that you have a laptop and internet connection. That's it. That's all you need. You don't need money. You don't need anything extra. So we're talking here about a global computer with storage, state, and atomic transactions, and a built-in consensus mechanism. As with the original disclaimer, some things are already working, some things are there, and people are playing with it and using it. Some things we are still working out. So, for example, all those systems, even IPFS being global, you know, how useful is that? Well, it is useful, but you know, IPFS being global means it's not only used by developers sharing dependencies, it's also used by anybody sharing anything, right? And then if you actually run the node, very quickly you realize that you know, your client kind of gets quite fat because you tend to store some things that you don't necessarily need to store. I was telling here that you don't need to store other people's work, but the way it is currently configured is that you will, right? You are kind of voluntarily participating in kind of like a BitTorrent where you're storing other people's stuff, right? You can limit the bandwidth and all of that, but with the global system, it's like it's very quickly unmanageable for the individual, right? So it might be easier if those systems are more constrained. So we say, I have a bunch of friends who are interested in paragliding, and we share some paragliding stuff. And it has nothing to do with dependency tracking or anything extra, right? And we have our own community, and we store our own stuff, and we don't pollute the global space. With the global space, it solves some problems. Like, for example, for dependency tracking, that's great that it's a global system. But it's not only for dependency tracking, it's for anything, right? Okay, so what is Ethereum? Well, Ethereum is a blockchain. It's the same as Bitcoin, which has internal currency. And it has a built-in virtual machine which executes pieces of code. And those pieces of code are written in a language that expresses the logic of what the code should do. And then you have different programming languages, and the more widely used one is called Solidity. It looks a little bit like JavaScript. It's very easy to program in it. It has a couple of keywords that you have to learn, and a couple of types, like, for example, address, that you don't have in typical, you know, Go programming or JavaScript, because it's kind of yeah. So programming what? Smart contract, right? But what is smart contract? Well, you have couple of terms. So first is smart contract. Smart contract is like a class which kind of has some behavior, and then if you combine them, then you will have a distributed application. So if you combine multiple smart contracts, you will have kind of a particular application to deal with. If you combine multiple of those, you have kind of a distributed, decentralized, autonomous organization. So it's sort of like a more automated system for achieving something bigger, right? And then if you scale it even further, you have something which is like a distributed institution, which uses multiple distributed organizations to establish norms and engagement and automate enforcement of those norms, right? So this is still in kind of a digital domain. Here we kind of crossing into something that humans use for achieving kind of different things than the digital realm allows. And then a smart contract is a single point of entry, kind of like an object or a class, instantiated class, with a life cycle and messaging input-output capabilities. So in a sense, it is kind of like an activity, okay? It has its own life cycle, and it can take messages in and send some actions out, and it is deployed in this global computer that nobody controls. Can you shut it down? Well, if you decided that you want to code something that you can shut down, it can be shut down. But if you thought, well, I want to have it run forever and nobody should ever be able to shut it down, then you coded it in such a way that it will never be shut down, right? So unless the blockchain owners decide to do something with the leftovers which people leave running there, it will be there forever, right? We do have this problem of garbage collection. We have a lot of spam and a lot of, spam, there is no other way to name it, which remains in the blockchain. And then there is no mechanism at the moment to kind of remove it. They are working on mechanisms for removing crap from the chain. But at the moment, it's a very democratized system, so anybody can put whatever they want. It will cost them a little bit of money, but it pollutes the millions of computers which are running the network. So programming smart contracts. As I said, we have slightly different storage models. So with IPFS, we store blobs in the global computing system, global drive, and we are not limited by space or anything. With the chain, we are very strictly limited by how much we can store, but the data can be updated, right? So if I stored something, it's more like a variable that I can change the state of. Whereas with IPFS, it's like a blob, which is immutable. Once created, it will forever be the same. It's just hashed piece of binary blob. So what is possible? Well, there is a number of things that you can code. So for example, how would you play rock, paper, scissors over internet? You could play on Skype, right? But then you would have to rely on the latency being kind of fair, right? If you pretend to have some glitches and just wait a little bit before you see the other person gesture, you can kind of cheat, right? So it would require a perfect synchronicity. Can you play rock, paper, scissors over email? No, right? But how could you play it via email? How can you modify it so you would be able to play it via email?
They both send an email to like a third party.
To Christopher, right? We say, okay, we both email Christopher with our choice, and then he sends us who win, right? Would it work? Yes, it would work. The problem is we have to trust him, right? I have to trust him that you didn't pay him to sort of tell you what I said before you sent him an email, right? So can we do that without Christopher? Can we play rock, paper, scissors over email without Christopher?
You can decide and then salt it and then hash it.
Yes, exactly.
The hash, and then you both send hashes, and afterwards you dehash and see if there's like your choices in the middle of that salted string.
Exactly. So did you understand the solution? We both decide what we want to do. We have some agreement of what R, P, and S means. And then if I said R, I will kind of salt it and hash it. And then I will announce my hash. And he will kind of salt it and hash it and announce his hash. Now those two things are public. I see what his hash is, but I don't know what he picked. And he sees what my hash is, but he doesn't know what I picked. And now we have to reveal the salt and the choice, right? And then by revealing the salt and the choice, we suddenly confirm who wins, who loses, right? Because it's fair. And he cannot change his mind, and I cannot change my mind because it's already salted and hashed. And that's how smart contract can allow you to play rock, paper, scissors. And that, is one of the existing smart contracts, right? So there is a contract which allows people on the internet to play rock, paper, scissors in a fair way without Christopher, without the trusted third party. It's just between two peers. And you cannot cheat because it enforces the rules as we just said, right? Okay, you can also have like alarm clock which triggers something happening on the chain, right? So there is a smart contract which is kind of you can set the time notification for somebody else to do something, right? The clock doesn't do anything. Instead, the clock just triggers something else. So the clock will call another smart contract to do something at a given time. Or
So the contracts are not autonomous in that sense, right?
that's right. So the contracts are not they have to be, they only react to external stimuli, right? They don't do anything on their own without somebody needing something to be done. So it's sort of like a service which waits there for input and only reacts to the input. Okay, oracles, yeah, that's hard. I will skip it. Yeah, so we have a number of things. Why we talk about the oracles? Because inside the chain, there is a limited amount of things that you can do. You cannot interact with the outside world. You can only do things which are kind of contained to the chain itself. So you need some mechanism for letting the contracts know what, for example, what temperature it is, or what current price of gold is. And those inputs into the contract from outside world are called oracles. There is a large number of distributed applications under that link. And there are some contracts which allow people to combine the resources for mining. And they are written as smart contracts as well. All right, so we're kind of running out of time. The rest of the lecture is about the Solidity, the language, and it kind of goes over some of the primitives and some of the types system and some of the way of programming and Solidity. Those of you who are interested, you can scan it. There are tutorials and documents on the internet as well. We will not have any questions in the exam related to the programming of smart contracts, but there might be something about smart contracts, like what is it for, and kind of general concepts, right? Those of you who are interested, we have a kind of a working group on smart contracts with some of the master students, and there might be a meetup for introduction to Solidity on 25th of April. In the evening. It has been posted on Facebook by other students. So if you're interested in this topic and to learn more about Solidity and so on, then follow up in your own time. Questions? Okay.
Why is there no way to interact with the outside world from the Ethereum network?
Because it's super costly. And also it would require a trust on the component which talks to the outside world, right? Currently, because it's all contained, you don't need to trust anything, and it's verifiable, and it sort of ensures that what your intention is, that's what it does. As soon as you kind of allow outside inputs, they can be forged, they can be manipulated and whatever, and it's harder to maintain a trustless kind of environment without additional things. So you can do it, but it requires, for example, a trusted third party. Again, you have to put the trust somewhere.
So the oracles are breaking the pattern, but they have to allow it, and they just have to restrict, what's it called, control it and make sure that it's being done correctly.
That's right. So that's what this was also the caveat. So we have not worked out all the science yet. One of the very interesting scientific problems is how to let a third-party computer compute something, and you being sure that what it computed is what you want it to be computed. Okay, so it's called multi-party computing models and kind of encryption schemes. For example, for you giving Christopher a piece of code, telling him, you run it on your laptop and give me the result, and you being sure that he really did calculated it and he didn't change the program in any way, right? Once we have those mechanisms being properly implemented, we will have oracles which are trusted internally by the verification systems. Currently, we don't have that yet. We have some, for some simple functions we can do that, but for more complicated ones we cannot. And that's kind of an ongoing research effort of how to achieve that. For static data, we already solved most of the problems. But for the dynamic computations, we don't. We haven't yet, but it will happen. We're making progress in the recent years. We're making more and more progress. So, for example, we've made progress of validating the signatures and making sure that some of the signing and hashing is done correctly in such a way that it cannot be spoofed, which means we now have Bitcoin-like systems with a perfect anonymity, because all the information which is in the ledger about the transactions, it's sort of hidden in such a way that it's verifiable but not demonstrably leaking any information, right? So that innovation happened like in the last few years, where we knew about how to do that. It was just extremely slow, not practical. And now we're getting to like generating a particular scheme takes on a modern laptop about 30 seconds, and then verification of it takes 50 milliseconds. So we're getting to kind of a models which are practical enough for practical applications. Yeah. Okay, thank you.